Great presentations. We have a few minutes for questions. Dr. Agee there in the front.
Yeah, these are some great talks. I was obviously interested in some aspects of it that I know about. And so I have two things. One that has to do with hematite. And it turns out that when we were looking at NWA 7034, we first thought it was full of hematite. But the hematite is actually not hematite, it's maghemite. And it has a small amount of water in it. And I'm just wondering if some of the hematite that people are seeing on Mars is actually maghemite.
Yeah, that's a great question. And we can resolve the difference between hematite and maghemite with Chemin. So we are confident in the hematite detection.
Right. Cool. Anyway, Hap, you need to add it to your list because it's in there.
I will, thank you.
And then the other thing has to do with the age of NWA 7034. It's not really 4.4 billion years old. It is a polymicted breccia, and it contains about 6 different lithologies, and it has sedimentary things in it, and it's got lots of things that we still don't understand. When we first age dated it, we had an RBSR age of 2.1 billion. Then we started finding zircons. And the zircons and apatites have a wide range but they cluster mostly around 4.4, but also there's a population that it's around 1.5 billion.
Right.
And so I would say actually that samples a lot of Martian history. And it may actually be consistent with some of the things that you were talking about with respect to water, more recent in Mars, because NWA 7034 is full of water. And I think some of the ages are actually quite recent.
Yeah, that's really why I said that may be the most important of all of the meteorites. It's not one sample. It's a conglomerate of samples, and there's a lot of work yet to do in pulling all the pieces apart.
Thank you both for really excellent talks. It's just fascinating. I have about 100 questions, but I'll only ask one. and that relates to the jarosite that you talked about that's been found. And yesterday we heard from Michael Schindler that, I believe he said, he's here somewhere I hope, that he found jarosite that was not requiring acidic conditions in some soil. And so I wondered, how firm are the conclusions about formation of jarosite based upon that?
Yeah, I would love to talk to Michael about the conditions of the non-acidic jarosite, but we do see other phases that suggest acidic alteration, like the Akagani I mentioned. So I guess, I didn't know that there were jarosites that formed in non-acidic conditions, so I'm definitely going to talk to Michael about that one.
Can I shortly respond to this? Jarosite was formed under acidic conditions, but was confined pore spaces. And when they lined the soils afterwards, it still existed in the confined pore spaces. So it exists in near neutral pH condition in soils, but it's confined and was formed under acidic conditions.
Okay. It formed under acidic conditions, but it remained...
In the confinement.
Okay.
After neutralization.
Okay. Oh, that's interesting.
Yeah,
Good question.
Can I add something to that too? Because I work with Michael. I'm Mike Rochella, Liz. I don't know if you know me or not, but great talk, Pat. Thanks so much. And also on the amorphous material that you reported, Liz, actually I'm not surprised at all. I would have been 15 years ago. Your amorphous materials and these kinds of rocks with these kinds of minerals at those pHs, amorphous materials are way underreported. In fact, for all intents and purposes, they're not reported except in our publications because we see it all over the place. And I can show you what we see and the elements that are there. These materials are silicon alumina rich. They definitely only have short range order. They're definitely amorphous materials. And they're also a collecting house for a lot of transition metals. So I can show you what we have.
Cool. Yeah, please. Yeah, during both of your talks yesterday, I was just like just taking notes about things I need to read. So thank you.
Use the microphone.
That was so awesome and interesting talk. I really like to hear all of this. I have 3 questions for Liz. So the first question is, you talk about the hydrothermal, possible hydrothermal condition on Mars. So how high is the temperature will you expect for those minerals to form? And the second one is, because on Earth we see a lot of goethite formed, but why there's not goethite formed on Mars? And the third question is, you studied the ritual structure analysis of those minerals. Did you see any significant differences of crystal structures between the minerals on Earth compared to the Mars?
Yeah, great question. So the hydrothermal question, we don't see evidence for high temperatures. So we think they're warm-ish, 50 to 100 degrees C maybe. The second question, remind me, was why no goethite? I don't know. We expected to find it, but maybe it has since transformed into something like hematite over those few billions of years that it's been sitting around. And then the third question was the crystal structures. With the plagioclase, that's the one where we're most confident in those crystal structures. We don't see a large change within the stratigraphy or between different samples, which is interesting, especially if we think that there would have been some evolution of these magmas. We see almost all just Andesine. Good questions.
I'm wondering if you can comment on 2 papers that came out maybe about 2 years ago about manganese oxides on the surface of Mars, and you didn't mention those in your talk, but if you could maybe tell us a little more about those.
Yeah. Oh gosh. Okay. So manganese oxides have been detected by ChemCam. ChemCam is an instrument that's on the mast. It performs laser-induced breakdown spectroscopy. So it does laser ablation and is measuring these rocks. And so the spot size of these manganese oxides is very small. Like tens to hundreds of microns. In some cases, they're coatings, but we have not detected any crystalline manganese oxides with chemin. But the implications are that they require incredibly oxic conditions to have formed.
Hematite, which may very well be maghemite. The absence of goethite is basically, the absence of goethite is pretty consistent when one thinks of the iron oxide equilibria, not in bulk phases, but in nanomaterials. And most of these are presumably quite fine-grained. The thermodynamics of nanophase iron oxides could very well sort of end up with maghemite as the stable phase, unless there's a mechanism for coarsening it, and at the low temperatures involved, there probably is not.
Yeah, we just published a paper about like a silica, actually 3 minerals. You will see cristobalite and tritiumite, orthorhombic tritiumite, and opal CT stuff. 3, based on the texture, it's more like a hydrothermal. You can see the boiling feature. So certain kind of precipitates definitely tell like boiling things. So the hydrothermal one could be those like usual. Lots of those silica polymers could be pretty high temperature stuff. That doesn't mean the original source could be like segmented, like transported to this particular basin.
Yeah, and what temperature were your deposits or samples from?
So in Hap's talk, he mentioned that the oxygen isotope signature of Mars is very different than Earth, that there's this totally different fractionation line. And I thought that was a really intriguing observation, of course, since oxygen is such an abundant element in the solar system. And so my question is that completely different fractionation line, you would think that if all the planets were forming from the same homogeneous pool of oxygen, that it would be the same fractionation line. Is that potentially a kind of an indirect piece of evidence that the Earth-Moon system did form from an impact that brought material from outside the solar system? Or are there other ways that you can get that deviation in fractionation line?
So the Earth and the Moon have practically the same, they lie practically on the same line, whereas everything else, well, actually there's a group of meteorites called the instatite chondrites that also lie on that line, which leads some people to think that the Earth formed from instatite chondrites. I think that's a little too straightforward, but if I showed you that diagram with all of the kinds of meteorites on it, you would see the whole diagram is populated by separate mass fractionation lines. And clearly the early solar system was not homogeneous in terms of its oxygen isotopic composition. There were clearly different reservoirs. It's a very powerful tool, though. And so, for example, one of the models that we use to get at the composition of the Earth, the bulk composition of the Earth, is you mix the different kinds of chondrites that you want to do that with, and the mixture has to give you the right oxygen isotopic composition, since all of these different chondrites represent different reservoirs. But it's a very powerful tool. It's also how we now identify Martian meteorites, because it's too hard to measure these trapped gases, but you can measure the oxygen isotopes really easy. So.
Oh, thank you. One more? Thank you, Doug. Just a note about the jarosite, if we can circle back to that. I've been running controlled humidity experiments on the reaction between clay and pyrite for the last 15 years or so. But one of the first minerals you form in that reaction is jarosite. You know, you don't need an acidic hydrothermal fluid or lake. You can do it fairly dry. Although, I've got to say, I've only been able to get controlled humidities down to like 53% relative humidity. So it's not exactly dry, but it's certainly not wet.
Yeah, no, that's a great point that, you know, maybe we don't need that much water to do this. We haven't found any pyrite. That doesn't mean it wasn't present. But yeah, maybe like a mechanism. So, you know, it's a 5 kilometer tall stack of sediments. There's phyllosilicates in there. There's smectites. Maybe as they're dewatering, you know, it's producing some fluids interacting with sulfides and precipitating the jarosite. So that's a great point.
Okay, let's thank our speakers for an out of this world session.